Hi, thanks for joining me. Today we're going to be talking about the second half of the Gauss-Markov assumptions. If you missed the first half, you might want to have a look at the previous video which looked through assumptions 1 to 3. So just to sort of reiterate again, the Gauss-Markov assumptions are the set of conditions which, if they're upheld, then that means that least squared estimators are blue. So that means that they're the best linear unbiased estimators which are possible. So the fourth Gauss-Markov assumption is something which we refer to as no perfect collinearity. And this is referring to our particular sample, but by sort of deduction it also refers to the population. But what does it actually mean? So no perfect collinearity in regresses, I should say. That means that if I have some sort of model that y equals alpha plus beta 1 times x1 plus beta 2 times x2 plus some sort of error, that there cannot be an exact relationship between x1 and x2. So there cannot be I cannot write down in an equation exactly that x1 is equal to delta naught plus delta 1 times x2. That means that if I know x2, I exactly know x1. In a sense, x1 and x2 are exactly the same event. So an example of this might be if I was trying to determine which factors affect the house price of a given house from its attributes, then if I was to include a regression which included the square meterage of that house and also the square footage of that house, well, obviously if I know square meterage, I actually also know square footage. They're both exactly the same thing. Square footage is basically equal to 9 times the square meterage of the house. So obviously in a regression, I'm going to have a hard time unpicking the effect of square footage from square meterage because they're exactly the same thing. And the assumption of no perfect collinearity in regresses means that I cannot include both of these two things in my regression. Assumption 5 is called homoscedastic errors. So homoscedastic errors means that if I was to draw a sort of process, so let's say I have my number of years of education and my wage rate, and this again is referring to the population data rather than to the sample. If I have errors which look something like, when I draw the population line like that, whereby the sort of distribution of errors away from the line stay relatively constant. They both sort of lie within these sort of error lines which I've drawn here. There's no sort of increasing in errors or decreasing of errors along with the education variable. Then that means that errors are homoscedastic. So mathematically that just means that I can write the variance of our error in the population process is equal to some constant sigma squared, or sort of writing it a little bit more completely, the variance of ui given xi is equal to sigma squared. In other words, the variance, how far the points are away from the line, doesn't vary systematically with x. The last Gauss-Markov assumption is called no serial correlation. And what this means is mathematically that the covariance between a given error ui and another error uj must be equal to 0 unless I equals j, unless we're considering the covariance of the error with itself, in which case we have a variance, which is sort of assumption 5. So this last assumption of no serial correlation means that the errors essentially have to be independent of one another. So knowing one of the errors doesn't help me predict another error. So in other words, if I know this error here in my diagram, that doesn't help me predict this error here for a sort of higher level of education. This concludes my video about the Gauss-Markov assumptions. I'm going to go and examine each of these assumptions in detail in the next few videos. I'll see you then.